objective in this video is to study product spaces. Given two metric spaces x and y, there are several natural ways to make x cross y, the Cartesian product, into a metric space. The issue is that since there are several ways to do this, which one is the correct one? To address this, we will first begin by studying the notion of equivalent metric spaces. We note that this is different from two metric spaces being isometric or something like that. This is a given metric space, or rather a given set with two different metrics, and we want to study when these two metrics can be considered the same. So we begin with a simple definition. This is the notion of equivalence of two metric spaces from the perspective of topology. Two metrics D and D prime on the set X are said to be equivalent if they generate the same topology. So the open sets in both metric spaces are exactly the same. Since convergence of sequences as well as continuity can be characterized entirely in terms of open sets, this is a natural definition of two metrics being equivalent on a given set. If rather we say D and D prime are strongly equivalent if we can find constants small c and capital C such that we have the following inequalities: c dxy is less than or equal to d prime xy is less than or equal to capital C dxy, and this should be true for all xy in x cross y. So let me just put it as a pair. Okay, so of course C is greater than 0 and capital C is also greater than 0. So the notion of strong equivalence actually subsumes the case of equivalent metric spaces. That means if this condition is satisfied, if this is true, then I ask you to show as an exercise that both D and D prime will generate the same topology. However, this notion of strong equivalence is in fact stronger, as the name suggests. To see that, work out this exercise. Given any metric space xd, show that d prime xy is equal to dxy divided by 1 plus dxy is an equivalent metric. Is D prime strongly equivalent to D? Is D prime strongly equivalent to D? Now, what happens is that this new metric that we have defined, dxy by 1 plus dxy, has the special property that it's a bounded metric. What I mean by that is, no matter what set you take, including the whole of x itself, it's going to be of bounded diameter. The diameter of any set in x under D prime is going to be bounded. Whereas that might not be the case in D. So you can take an infinite set and you can find this equivalent metric D prime in which that set will become of finite diameter. Now, why this is interesting is Cauchy sequences between D prime and D may not be the same. It could happen that a particular sequence is Cauchy in D but not in D prime, or vice versa. I want you to investigate such aspects. Nevertheless, if xn converges to x in D, then xn will converge to x in D prime also. So convergence of sequences will be the same, but not necessarily Cauchy sequences. So strongly equivalent metrics in some sense preserve all properties of metric spaces, including things like boundedness and completeness, which we will come to in the next future videos. Strongly equivalent metrics will preserve all such properties, whereas equivalent metrics will preserve only the topological properties, those that can be characterized entirely using open sets. Okay, so there are these dual notions depending on what you are interested in. If your primary interest is topology, then equivalent metrics are enough. On the other hand, if you are interested in aspects that are more analytic in nature, like completeness, you might need to consider only strongly equivalent metrics. Okay, now let's see a concrete example. Rather, I will leave it as an exercise to you. Exercise again. Let xd and yd prime be two metric spaces. Define for P equal to xy and Q equal to uw the following: dE of P comma Q is under root d of xy squared plus d of there's a slight mistake here. This is under root d of xu squared plus d of yv square. Okay, E here is supposed to be an abbreviation to suggest Euclidean, because this is the way the standard Euclidean metric is defined on R2, starting with the absolute value on R. The second one, d max of PQ, is just d of maximum of d of xu comma d prime. Here again it should be d prime here, so just note that there was a small mistake here. This is supposed to be d prime. So max of dxu comma d prime yv. You just take the maximum of the two as the name suggests. And the third one is the d sum of PQ is, as you could expect, d of xu plus d prime of yv. Show that all of these are strongly equivalent in x cross y, right? So given two metric spaces xd and yd prime, here are three natural ways to make the product into a metric space. It turns out that all three of them are strongly equivalent. So from the perspective of studying sequences, continuity, Cauchy sequences, completeness, etc., all of these metrics can be interchangeably used, and we will use that metric which is most convenient for the situation. Please note that these three definitions we have already given in the context of Rn, Euclidean space. Okay, these three metrics obviously have extensions to finite products. You extend it in the most straightforward and obvious way. All these are thankfully strongly equivalent. So when we are doing analysis in the Euclidean space Rn, we can use any of these metrics depending on what the situation demands. Okay, and of course, as you can see, as I have mentioned before, and which you should check, is that Cauchy sequences in x cross y under all these three coincide. Okay, now there is another property which is interesting with these a choice of metrics, also show that xn yn converges to xy in x cross y if and only if xn converges to x in x and yn converges to y in y. This is true under any of the three metrics that we have defined. Okay, so what this is essentially showing is that when you choose these strongly equivalent metrics, you can characterize convergence of a sequence in terms of the behavior of its components. Okay, also show the same thing for Cauchy sequences. I'm not writing out that exercise, it's there in the notes. Show that xn yn is Cauchy if and only if xn is Cauchy and yn is Cauchy. Okay, so finally one more exercise to reinforce the understanding of equivalent and product metric spaces. Let xd be any metric space. Look at the function d from x cross x to r. Okay, the actual metric is essentially a function from the product space to R. Now put any of the metrics in the previous slide. And show that D is continuous. So when you consider X Cartesian product with itself, you have these three natural metrics that we have defined. Under any of them, the metric itself, D, would be a continuous function. Okay, now we come to the central theorem of this short video. It is essentially saying that the choice of metric doesn't matter, at least from the topological perspective. So here is the theorem. Let x d1 and y d2 be two metric spaces. Also, we equip x cross y with a metric D with the property that xn yn converges to xy in x cross y if and only if xn converges to x and yn converges to y. Okay, then the claim is that you can completely characterize the topology of x cross y just from the data that you have put a metric with this characteristic property, the natural one that you would expect from a product space, that a pair of sequences converge if and only if component wise they converge. Then the open sets in x cross y are precisely the unions of products u cross v, where u subset of x and v subset of y are open. So what is this theorem trying to say? It's just saying that if you take a product of two metric spaces and put a metric on that product which has this characteristic property that you would expect, that xn yn converges to xy if and only if xn converges to x and yn converges to y, then you can immediately write down what the open sets in x cross y are going to be. They are precisely the products u cross v, where u is an open set in x and v is an open set in y. Consequently, what this is indirectly showing, or rather directly showing, is that you could have put whatever metric you want on x cross y, as long as it has this property, it's going to be equivalent to any other metric with that property. So two metrics on x cross y that have this characteristic property, they are equivalent to each other. So in some sense, it really doesn't matter what metric you put on the product space from the perspective of topology, simply because they are all going to lead to exactly the same open sets. Now the proof has some nice ideas, so please grab a hot beverage and put on your seat belts. So what we do is the following. Let E subset of x and f subset of y be closed sets. You will understand in a moment why we are choosing closed sets. It's sort of understandable because we have the key property in terms of sequences, and closed sets are in fact defined using sequences. So it's sort of natural to expect that closed sets will have a role to play. So if xn comma yn is a sequence in x cross y such that xn yn converges to xy in x cross y, then, well, we have the characteristic property xn converges to x and yn converges to y. Yn converges to y. Okay. Now, let me just make a small change. Xn yn is in E cross F. Otherwise, what was the point of picking these closed sets? Okay. What is this? So, because E and F are closed, we must have X is in E. Hence, X is in E and Y is in F. That's just because E and F are closed sets. Consequently, x comma y is there in E cross F. Okay. What this shows is that E cross F is closed. The product of a closed set in X and a closed set in Y is going to be closed simply because we have shown that if you take an adherent point xy of E cross F, then that adherent point is there in E cross F. Okay. Now, how does this help? We have shown that the product of two closed sets is closed. How does this help? Well, let's consider U subset of X and V subset of Y be open sets. Take two open sets. Now, the first goal is to show that U cross V is also open. Ultimate aim is to show that given any open set, it can be written as a union of sets U cross V. First, let's see that U cross V is open to begin with. Okay. Now, the way to do that is we know that closed sets continue to be closed when you take product. So, we are given open sets. So, it's natural that we try to consider complements and take open sets and see what happens. Now, X itself is a closed set. You can take X cross Y set minus V. Okay. Now, V is an open set, therefore Y set minus V is a closed set. So, this is closed. This is closed. In an entirely similar way, we have X set minus U cross Y is closed. Okay. Both these sets are closed. Okay. Now, that means the complements of these two sets must be open, right? What are the complements of X cross Y set minus V and X minus U cross V? Well, they are nothing but X cross V and U cross Y are both open, taking complements. Okay. Well, that means the intersection X cross V intersect U cross Y, which is nothing but U cross V is open. Okay, that was rather easy. What we have done is, by using the fact that closeness is preserved by taking products, we have shown that openness is preserved by taking products. Okay. Now, what is our goal? To show that if G subset of x cross y is open, then G is a union of sets of the form U cross V. U subset of x, V subset of y are open. Okay, this is our ultimate goal. Now what we are going to do is the following. We are going to take a pair x comma y, which is there in G, and what we are going to do is we are going to find U comma V, x is in U, y is in V, and U cross V is subset of G. Okay, just a 30-second thought will convince you that this is more than enough. All we are doing is, given any point in G, we are squeezing a product U cross V between that contains this point and is contained in G, and this will show that G can be written as a union of sets of the form U cross V. Suppose not. Well, what does this mean? This means that if you consider B x 1 by n, Cartesian product B y 1 by n, these are the open balls in x and y respectively, this is not going to be a subset of G, no matter what n we choose, right? Because we are assuming that it is not possible to squeeze a product of open sets within G that contain the point x comma y. If you take these particular balls of radius 1 by n centered at x and y, it's not going to be contained within G. So no matter what choice of n we choose, no matter what the choice of n. Okay. Now, what does this suggest? Well, let xn comma yn be an element of Bx 1 by n Cartesian product By 1 by n. So essentially we are taking a sequence, which is ultimately what we should be doing, because the hypothesis is entirely on the behavior of sequences. So take this sequence xn comma yn, which is coming from the ball of radius 1 by n centered at x, Cartesian product with the ball of radius 1 by n in y. Now obviously xn converges to x, and I made a slight error. Actually, it's not an error, it's more of an omission. Don't take coming from bxn cross by 1 by n. Okay, what I'm saying is take it in, let xn yn be an element of this set minus g, right? I'm taking a sequence which is there in the product of these balls, but this sequence, the elements of this sequence are not in G. Why does such an element exist? Well, because look at our hypothesis. We are saying that this product is never going to be a subset of G irrespective of the choice of n. So for each n, we can at least find one element which is there in Bx 1 by n cross By 1 by n, which is not there in G. Okay, so choose this sequence xn yn, which is there in Bx 1 by n Cartesian product By 1 by n set minus G. Well, obviously xn converges to x and yn converges to y. That's exactly the way the sequence has been constructed. Okay, now our hypothesis says xn yn must converge to xy, right? Whenever you have components converging, then the product sequence must also converge. Okay, but x cross y set minus G is open because is closed because G is assumed to be open. Okay, so x Cartesian product y set minus G is closed, but we have just seen that xn yn is a sequence in x Cartesian product y minus G. Remember, because that's the way we have chosen this sequence xn yn. This means xy is an element of x cross y set minus G, right? Because this is a closed set. But this is nonsense. We started off with a point in G, and we are ending up with the stupid conclusion that this point is not there in G. Okay, so this proves the theorem. Our assumption that more specifically, this assumption that you cannot find open sets U and V such that U cross V is subset of G and X comma Y is there in U cross V is untenable, and therefore the result is proved. So we have this nice characterization of product metric spaces when you have this key characteristic property that Xn Yn converges to Xy if and only if Xn converges to X and Yn converges to Y, if we have this property. Okay, so what does this tell us? This sort of tells us that the metric of choice does not really matter if you're really interested only in the topological properties, or if you're rather interested only in the open sets. It really doesn't matter which metric you choose. This is a course on real analysis, and you've just watched the video on equivalent metrics and product space.